It is a pleasure to introduce our first speaker this morning, Professor Ilaria Colazzo from University of Leeds. She will tell us about matched pairs of groups and the combinatorial solutions of the pentagon equation.
Thank you very much for the introduction. Let me try and share my screen. Okay. Okay. So thank you very much for the introduction, and thank you very much for having me here in this very nice conference. So what I want to talk about today is the relationship between matched pair of groups and combinatorial solution to the pentagon equation. I will explain exactly what all the words in the title will mean during my talk. So first of all, why I'm interested in why the pentagon equation is interesting. So a little bit of motivation. So the pentagon equation is very similar look-wise to the solution to the Mach equation that you can see here. But as you can notice, this is less symmetrical. This is a very important equation that appears here and there in various areas of mathematics. From mathematical physics, has been proved that the pentagon equation provides solution to the tetrahedron equation, which is a higher version of the higher dimensional version of the Yang-Baxter equation. In Hof algebras has been proved that the pentagon equation plays for the Heisenberg double the same role that the Yang-Baxter equation plays for the Drinfeld double. And also fusion operators in monoidal categories that satisfy the pentagon equation. This just to name a few areas where this equation appears. The perspective that I want to take on the solution of the pentagon equation is slightly different. I want to study the pentagon equation in the category of sets. And this will allow me to use more combinatorial tools, like, for instance, group actions, to study this equation. So what is a set-theoretic solution to the pentagon equation? So it's a pair of capital S, where S is a non-empty set. I usually will take this set to be finite, but some of the results that I will present also hold in the case in which this set is not finite. And S is a little s is a map that maps pair of elements of my set into pair of elements that satisfy in S cross S the pentagon equation. So the equation that you can see here in the screen. What does it mean to the Sij map? This is a map that maps tuples into tuples and acts as S on the entry Ij and as the identity on the remaining entries. So for instance, S12 will be the map S cross the identity. So now let's us frame the problem. The problem is I want to describe to find a description of all solution of the set-theoretic solution of the pentagon equation. And I want, since this seems to be a little bit wide as a name, I want to restrict myself to the case in which the map little s is bijective. And now from now on, when I will speak about solution, I will always mean that I'm referring to set-theoretic solution to the pentagon equation. So I will say solution, but what I really mean is set-theoretic solution to the pentagon equation. For the content of this talk is basically based on two joint work, one with Erik Jespers and Łukasz Kubat, where we obtain a complete classification of involutive solution, and where involutive solution means that the square of my map S is the identity. So it's a little bit more than being bijective. The inverse is the map itself. And in this case, we obtain a classification of this solution without any restriction on the cardinality of the set S. So our classification works also in the case in which S is not finite. And the other joint work is with Jan Okniski and Arne van Antwerpen. And here we obtain a classification of bijective solution. And there are some places where we really use the finiteness of the set S. So, which is the how we can approach this? So we said that if we have a solution of the pentagon equation, set theoretic solution of the pentagon equation, this is basically a set and a map that maps pairs into pairs. Now I want to find a convenient way to express the image of the pair XY. And the image of the pair XY for me will be given by a pair, of course, where the first component, I want to identify the first component using a binary operation from S cross S to S. And the second component, I want to use a bunch of theta maps that will be connected in some way. And why this kind of choice in describing the image of the map S? Well, because if we spell down what being a solution to the pentagon equation means, the first thing that we see, just writing down exactly what it means to be a solution to the pentagon equation, the first thing that we notice is that the binary operation that I defined on the first component is indeed associative. And then we see that the relation occurred in this theta map. Well, this theta map behave more or less like an homomorphism, but not quite, because we can see here that appeared in x dot y. So, and moreover, since we are interested in bijective solution, we want to see how this reflect on this bunch of theta maps. And what we can see is that if we write down what it means to be a bijective solution, then this property 3 will tell us that if I compose two theta maps, I still get a theta map. So somehow we find two structures that are closed under some binary operation. One structure is the set S with this binary operation dot, and the other structure is the set of all theta maps with the composition of functions. So the first thing that we can notice, because of property 1, which is that the operation dot is associative, is that if we really want to find some solution, better that we start with a structure that is associative. So, well, the first thing that comes to our mind is to start with a group. This is for sure associative, even more, but it's associative. And then, since I don't want to worry too much about condition 2 and 3, let's pick all the theta maps to be the identity. Then with this choice, it's easy to see that condition 1 is satisfied because we have a group. Condition 2 and 3 are trivially satisfied because all the theta are the identity. So we define a solution to the pentagon, a set theoretic solution to the pentagon equation. Moreover, it's not hard to prove that this is also bijective. The probably more surprising result is that if I insist that my set is a group, and I insist that my map is bijective, my map SG is bijective, then the solution defined in this way, where the theta map are all the identity, is the only possible bijective solution that I get on a group. Bear in mind, not up to isomorphism, really the only one that I can build. There are some results where the Catino, Mazzotta, and Miccoli obtain a classification in terms of subgroups of all solutions constructed on the set S being a group where they drop the assumption that the solution that they are looking for is bijective. So, but we are interested in bijective solutions, so having a group might be a little bit too much. So we would like to relax a little bit the assumption to have a group. So let's see how we can do that. So instead of starting with a group, I start with two groups. And I assume that, so two group A and G, and I assume that my group A acts on G by automorphism. So basically what I'm saying here is that I could consider the semi-direct product between the group A and G. And then I want to define a binary operation that is associative, but that is a little bit less strong than a group. And I would like to define this on the Cartesian product of A and G. And how do I do this? Well, I consider the product of two pairs, and what I'm secretly considering is many copies of the group G indexed by the element of the group A. So something like this. I have many copies of my group G indexed by the element of A. And how I want to perform the multiplication here? Well, the first component of the first element decide in which copy of the group G I'm working on, and then I will perform the multiplication in this group here. So basically, A comma G dot B comma H will be A, that says in which group G we are, and then just the product of G and H. It's not hard to convince ourselves that this operation is associative. And then I want to define my theta map, and my theta map, we remember that the second property obtained by saying what is a solution to the pentagon equation said that my map theta should look like an homomorphism. So what I want to do, I want to use this action here to define my theta map. And this is how we define it. So we have in the second component appearing this action sigma, and then we take the product of B and the inverse of A, this for technical reason. And then it's not hard to see that, of course, we prove that this operation is associative, so condition one is satisfied. And the second and the third condition follow from the fact that I have an action and a group operation. So this gives me a bijective solution. I can check that this is bijective. And the question is, okay, very nice. This is an example, but I would like to find a more interesting or involuted example. How can I do that? So my idea is that I want to follow, I want to stay in the same kind of direction of considering group connected in a semi-direct product way. And a natural extension of this concept is considering matched pair of groups. This definition might look a little bit daunting, but very second is something that we already encountered in our life multiple times. So a matched pair of groups is well, I have two groups, G and A. I have a left action of the group A on G, and this is not an action by automorphism. So I'm landing in the symmetric sim G. I have a right action of G on A, again in the sim, and then I have some kind of compatibility between these two actions. So when I act with sigma on the product, instead of being an automorphism, I see the right action appearing in the index. And the same in the same situation, we have the same situation for the right action rho, but now this condition is kind of the symmetric condition on the previous one. And it's not hard to convince ourselves that if we have a matched pair of groups and we define on the Cartesian product GA a product using these two actions here, well, what we get is a group, and this group is called the matched product of groups. And can we see some example of these things? Of course, all semi-direct product are particular case of matched product of groups. Indeed, it's enough to consider all the right action equal to the identity. And then what we get is that the condition 1 in the matched pair of groups will tell us that the sigma now is define an action by automorphism. The second condition is obviously trivial. So all semi-direct products are matched product of groups. But more, if I have a group H that emits an exact factorization, meaning that H has two subgroups, G and A, whose intersection is trivial and whose product is everything, meaning that if I pick any element in my group H, sorry, there is a typo here, this is an H. If I take any element in my group H, then there is a unique pair, an element in G and an element in A, such that my element X is the product of these two elements. So if I am in this situation where I have an exact factorization, then I can naturally define a left action and a right action using the fact that if I start with a pair of element A and G, A in A and G in G, I have a unique way in which I can swap them. And these will define exactly my left and right action. Then using this definition, I can prove that given a group with an exact factorization, I always have a matched pair of groups. And this kind of concept works in the other way around. So all matched pair correspond to exact factorization of groups. So if you want to think about a very concrete example of a matched pair of groups, you can think about A5, and A5 admits an exact factorization given in this way, where clearly none of these two groups is normal. So this is a genuine matched pair of groups. So why I care about matched pair of groups? Why this helped me to construct solution to the pentagon equation? If I start with a matched pair of groups, I can define on A cross G a solution. And my idea is that I want to mimic what I did for the semi-direct product. So the dot here is exactly given in the same way. I use A just to I use the group A just to choose the copy of the group G where I want to perform the multiplication, and then I want to use these two actions to define the theta map. And remember that now we don't have an action by automorphism, so somehow we expect that also the right action plays a role here. This gives me, it's a little bit involuted, but one can explicitly check that this gives a solution to the pentagon equation, and this is also bijective. Very nice. Now I gave you plenty of example of solutions, but why I want to go so far and using matched pair of groups. So I gave you a lot of example of solutions, but how far I am from the general case. So a really interesting fact, and to prove this here, we really use the fact that the set S is finite, is that if I start with a bijective solution, the product, the associative operation that I have on the set S always look like what we saw up to now. So a bunch of copy of the group G and indexed by a set of elements that is the set of idempotent element in the semigroup S. And the product will always look like this. And another interesting fact is that if I want the solution to be bijective, well, then all the theta maps have to be bijective. And now, since we are in this setting, my idea is that, okay, I computed with a computer a lot of example of the pentagon equation, and I saw that somehow many of them looked more or less the same, but had kind of a lot of thin hair, like a lot of repetition in my theta maps. So I want to get rid of all this extra information that I don't need. So I want to define a congruence on the semigroup S to describe all the bijective solutions. So I say that two pairs EG and FH are in relation tilde one to the other if the group element is the same. So the element in G is the same. And then if I look at the theta corresponding to the idempotent E and F, so theta E1 and theta F1, they are the same. Then one can check that using this, if I have a solution, bijective solution, and I consider this congruence on the set S, then I have a new solution on the quotient S over tilde. And I call this solution the retract. And this is interesting. Why? Well, because if I look at the retract, all the theta maps that I have in the retract, they are all different one to the other. And remember, they were all bijective. Then the other thing that I have is that I can identify one of the idempotents where this theta map is exactly the identity. And since all these theta are different one from the other, if we remember how was defined the congruence there, well, this is clear. It's clear for us to see that this I cannot perform a retract another time. So the retract is retractable. And now the crucial point here is that I want to deal with bijective solutions. So if I look at the bijective solution, I take the inverse. Well, this looks like the pentagon equation, but in the reverse order. And then if I use the same trick as before, I can define a bunch of psi maps and a binary operation. And if I spell down what this means, I get, look a little bit here, exactly the same condition that I got for the solution of a pentagon equation. So every time that I have a bijective solution of the pentagon equation, I can consider also the inverse, and this somehow give us a new solution to the pentagon equation using this trick in which I'm swapping this operation here. And now we can put all together. And if I start with a solution that is retractable, so basically I'm start from any solution, I take the retract, then I can apply everything that I saw up to now, and I can see that if I look at my solution, this will be a bunch of idempotent and a group part. And then I can define a left action using the theta map. And basically what I'm doing, I'm using the theta map, but only on the element in A and in the element in G. And I can check that this define a left action. And then I can look at this new solution associated to S with the solution T, and I can play the same game. And the very surprising point is that now the set A and the set G swap their roles. So the set G will take the place of the set of idempotent, and I have a group structure on the set A here. And then I can define, using the same trick, a right action. And these are compatible. So basically what I did, I started with a solution to the pentagon equation, or a retractable solution to the pentagon equation. I got a matched pair of groups using the trick that we saw in the previous slide. And then I can check that my original solution is actually isomorphic, where isomorphic means what you can think of is isomorphic to the solution associated to this matched pair. So basically what we said up to now is that if I start with a matched pair of groups, I can construct a solution, a bijective solution, which is irretractable, and vice versa. If I start with a retractable solution to the pentagon equation, which is bijective, I can define a matched pair of groups. And isomorphic matched pair of groups correspond to isomorphic solutions, and vice versa. So now we are almost done, because now we describe only a retractable solution. So all the retractable solutions are exactly the same thing as matched pair of groups. And what is left is, well, I overlooked some properties when I considered the retract. How can I lift my solution now back? So I start with any solution. I consider is retract, which means secretly I'm considering a matched pair of groups. And then what I can prove is that exists a non-empty set and a bunch of permutations, these 5 here, which are not, there is no condition on this much of permutations, such that I can identify my set S as a Cartesian product of X, A, and G. The multiplication here is basically only the multiplication on G, and I have X cross A copies of G. And then the data map is defined here as we define the multiplication for the matched pair of groups. And then I have the first component that is adjust using this bunch of permutations. But then this gives me all possible solutions without caring about being up to isomorphism. And then if I reduce my attention, if I only care about solution up to isomorphism, I can prove, and this is for me quite surprising, I can prove that this bunch of psi maps don't really play any role. So I can pick all my psi maps to be the identity. So my solution looks exactly like this. The product depends only on the group G. The multiplication depends only on the multiplication, the theta map depends only on the solution associated to the matched pair. And then what I'm adding here, it's basic, is fresh air. I'm adding alpha here and beta here. And this is not much more than this. This is everything I wanted to say. Thank you very much.